Hi, my name is Alejandro Ramirez.
My name is Mangulabnan.
Hey, my name is Asmay Gharia.
My name is Alyse Gonthier, and this is our study of biomechanics of stem cell differentiation.
We are analyzing the environmental biomechanics of stem cells, looking at how external forces lead to the differentiation of stem cells during growth. Our analysis stems from the 2011 Fu paper where stem cell differentiation was observed on multiple similar surfaces with different stiffnesses. Specifically, these surfaces were comprised of many cylindrical post-like structures of varying height. Taller posts had more ability to bend in response to applied forces and controlled relative substrate stiffnesses when in contact with cells. Figure 1 demonstrates how stem cells are more likely to differentiate into bone cells on a stiffer surface and fat cells on a less stiff surface. This method of studying cell differentiation in relation to environmental elasticity relies on modeling a cell on top of a substrate, as seen in Figure 2, taken from Matrix Elasticity Direct Stem Cells Lineage specification. Understanding this phenomenon is important because it can be used to help create an incubation environment where stem cells can be grown and differentiated into various adult cells simply based on the surface they are raised on. There is a wide range of potential applications from stem cell differentiation on regulated scaffolds like these, ranging from classical research to clinical settings. This could include growing specific cells for tissue growth, tissue or organ transplant, or specialized cell studies. For our analysis, we model a cell inside a substrate instead of on top of the surface.
Using COMSOL, we are creating a physics simulation demonstrating how cellular bodies are affected by the surface they grow on. Polydimethylsiloxane, or PDMS, is a common material used for such scaffolds because it is a relatively stiff, inert, and non-toxic silicone polymer well suited for cell growth inquiries. In our model, a cell has its weight supported by contacts in a box. A stiff matrix cannot deform much around a cell, so we approximate this as a box with fewer contacts. A softer matrix can bend around a cell and there will be more contact points.
This stem cell only has very few contacts with this surface because it's a very stiff surface. However, when this cell is done differentiating, it will become an osteocyte because it was in contact with a stiff surface. In a less stiff environment, the cell will make more contacts with the surface because of deformations. In response to this less stiff environment, the stem cell is differentiated into adipose tissue.
To simplify the process and create a working 2D model, we utilized the paper Elasticity of Human Embryonic Stem Cells as Determined by Atomic Force Microscopy, so that we could make their same variety of assumptions regarding the material's properties and maximum stress values. This includes a Young's modulus of 5 kilopascals, a Poisson's ratio of 0.2, and a density of 27 picograms per femtoliter, and the force per contact point as the force due to the weight of the cell divided by the number of contact points to ensure that the cell is in equilibrium with the environment.
Using our COMSOL model, we found that stresses on the cell were indeed better distributed on environments where the scaffold had a relatively low elastic modulus. In Mosavi and Dawider's 2015 paper, they established the strong correlation between cell fate and environmental stiffness, which points to the conclusion that mechanosensing of stress distribution is a major driver of differentiation. We have a variety of assumptions about the stresses on the cell. We must assume that all forces can support the weight of the cell. These contact forces yield a normal stress that is equal to the force divided over the area. There are no initial shear stresses in our model. COMSOL solves for stresses through the material given these boundary conditions. Applications of this include creating more specialized scaffolds or surfaces with finely tuned stiffness, either by polymer composition or microstructures, to increase specialized differentiation yield of induced pluripotent stem cells when creating tissues for patients. This can lower the cost of everything from skin grafts to emerging treatments like neuron or bone marrow replacement, as well as decreasing risk of tissue rejection from the host cells.
Some continuing questions that we have are, does the cellular differentiation occur in a hydrostatic environment where similar pressures are affecting the samples? How will the yield be affected while trying to harvest cells from matrices of varying stiffnesses? And is there a way to speed up differentiation of the stem cells?